Hello, and welcome to the video accompaniment for Chapter 5, Section 1 of our text. In this video, we'll be talking about relations. If you haven't yet, make sure you read through this section, familiarize yourself with any definitions, and maybe look at a few examples. What I'd like you to get out of this video, what I'd like you to be able to do after watching this video and reading through the section, is to be able to express and convert between the following four different kinds of representations of relations. So as a subset of a cross product, remember that's the definition of a relation. It's a subset of a cross product. As a list of relation between elements, we could just list out which elements are related to which elements. We could build a diagram that depicts the relation. And then also we could express a relation by defining a formula, so giving a condition under which one element should be related to another element. So we'll need to be able to swap between those four things. And so we'll talk about how to do that in this video. Also, I'd like you to be able to recognize these three properties of relation. So a relation might be reflexive, symmetric, or transitive. It could be any one of those. It could be none of them. It could be all three of those. Something special is going to happen when it has all three of those that we'll get to in the next video. All right, let's get started. So there are a few ways one can define a relation from one set to another set. And ways to represent that. So we'll take this relation, for example. So A will be our set containing the elements 1, 2, and 3. B will be the set containing -1, -2, and -3. And we're going to define this relation from A to B by A is related to B. Remember, this is our notation that says A is related to B. Remember, a relation is like a pairing of elements, where the first coordinate comes from A and the second coordinate comes from B. In that sense, right, a relation is just a subset of the cross product. Everything in a relation looks like a pair, where A is in A and B is in B. It doesn't have to be the whole cross product, A times B, just some subset of it. And so we're defining this relation from A to B. We say A is related to B if A minus B is even. So this is a particular instance of a relation, right? There's a lot of different relations I could have between A and B. In this case, I'm defining the relation. I'm defining A is related to B if A minus B is even. So this is what I would consider like a formulaic way to express a relation, or a formulaic way to represent a relation. I'm telling you a rule that assigns every element of A an element of B. The rule here is, if I take A and subtract B, if that's even, they're related. If it's odd, then they're not related. And so while formulas are nice ways to define relations, sometimes it's a bit hard to see what the relation actually is, what's going on with the relation. So this is why we have these other representations. So I'll go through a few of these. As a subset of a cross B. Let me erase that. Sometimes my hand doesn't do what my head wants it to. Subset of A cross B. So we'll think of the relation R as a subset of A cross B. All right, let's do that. Remember, this is really the definition of a relation. It's a subset of the cross product. And so in this case, let's write out R. This will be a good way to just get a handle on, do we know how to tell if A and B are related? Okay, so let's just run through all the possible pairs, right? We know the entire cross product. We know that A cross B will have cardinality 9. So it's possible I could have up to 9 different relations between elements. 9 different pairs of elements. So let's start with just picking out the element 1. What is 1 related to in B? Well, let's test. So we'll compare 1 to -1. And the rule is, if A minus B is even, they're related. If not, they're not. So 1 minus -1 That's 2, which is even. So this means that 1, -1 is a member of the relation, that 1 is related to -1. We'll go 1, -2, 1 minus -2, that gives me 3, which is odd, and so 1, we can say 1, -2 is not an element of the relation. So I'm not going to write it over here when I'm describing my set R. 1 and -3 though, 1 minus -3 gives me 4, which is even, and so 1 and -3 are related. All right, let's move on to 2. 2 minus -1 is 3, that's odd, so that's not in there. 2 minus -2 is 4, so 2 and -2 are in there. And then we need 2 and -3. 2 minus -3 is 5. That's odd, so it's not related. Those two aren't related to each other. And then finally with 3, 3 minus -1 is 4, so 3 and -1 are related. 3 minus -2 is 5. That's odd, so 3 and -2 are not related, and then 3 and -3 are. And that's all of them. I went through all the different possibilities. And so that is my relation, so we can see exactly what is related to what else. So another way you might do this is, instead of writing it as a set, you might just list out all these pairs of elements that are related. So for example, you might say 1 is related to -1. 1 is related to -3. I'm going to go ahead and put the second coordinate in parentheses. 2 is related to -2. That's what this notation means. 3 is related to -1, and 3 is related to -3. So that's another way you might define this relation. It's by just listing all the pairs of elements that are related. And so these two ways of representing relation are very similar. One, we can see just R is a subset of the cross product. Down here, I'm just telling you which pairs of elements are related in an exhaustive list. Another really helpful way to represent a relation is through a diagram. So I'm going to draw my two sets as blobs, as we always do, or potatoes, as an old graph theory professor of mine would call them, these potatoes. So this is the set A. Here's the set B. And just like we're doing a Venn diagram, I'm going to plop down my elements. So let's call this one 1, 2, 3. And over here, I'll plop down my elements as well. -1, -2, -3. And now I'll draw the relations. I'll draw an arrow from A to B, from an element A to an element B, if A is related to B. So looking up here, 1 is related to -1, so I'll draw an arrow from 1 to -1. 1 is related to -3, so I'll draw an arrow from 1 to -3, and so on. 2 is related to -2, but none of the others, so that's the only arrow from 2. And then 3 is related to -1 and -3 as well. So I'll draw those arrows. And here's our relation depicted in a diagram. And so this is sort of a helpful way to just visualize the relation. When we start talking about properties of the relation, there'll be things we can recognize in these diagrams that tell us about the properties. This will also be helpful when we define what a function is, which again is a special kind of relation. So we'll look at equivalence relations, that's a special kind of relation. These certain properties are going to hold. And then on the other hand, we'll also have functions, which are a different special kind of relation. And there's properties associated with that too. All right, let's keep moving on. So when we define relations, normally we talk about a relation from a set A to a set B. But in certain situations, we'll want to talk about a relation just on a set itself. So that is from a set S to itself, from S to S. It's just a special kind of relation when A and B are the same set. So let's take a look at a relation on a single set. So define the relation on the set S by A is related to B if A times B is greater than or equal to 0. What I'll do for this one is I'm just going to list out what's related to what by listing the elements of the relation. So R, let's run through the possibilities here. Now I'm relating the set S to itself. Notice that the cardinality of S is 1, 2, 3, 4, 5. So the cardinality of S cross S would be 25. So at most I'll have 25 elements in here, but probably not all of them. So let's see here what's related to what. I'll start with -2. And the relation here, what tells me if they're related is if their product is greater than or equal to 0. So -2 would be related to -1. -2 would be related to 0. I skipped itself. -2 is also related to itself, right? -2 times -2 is positive. Let's see, -1 is related to -2. -1 is related to itself. -1 is related to 0. And then what all is related to 0? So my rule here is that if the product of the two elements is greater than or equal to 0, they're related. Since the product of 0 and any other number is 0, that'll satisfy the condition. And so 0 should be related to every other element. So -2, sorry, I'll write I should say 0 is related to -2. 0 is related to -1. 0 is certainly related to itself. 0 is related to 1. 0 is related to 2. So 0 is related to every single element in the set. Notice something that you do really have to run through all the possible pairs. So like 0, -2, and -2, 0, these are two distinct elements, right? These are ordered pairs. Those are different elements, and they're both part of the relation. So make sure you're checking all possible ordered pairs in S cross S. So moving on to 1, well, I know that 1 won't be related to -2, 1 won't be related to -1 since that product will be negative. However, 1 is related to 0. 1 is also related to itself. And 1 is also related to 2. And lastly, we have 2. So let's see. 2 multiplied by any negative will be negative, so that's not related to those. However, 2, 0, 2, 1, and 2, 2 all satisfy the condition that their product is greater than or equal to 0. And so that's the relation. That's one way we could depict that is by writing it out. And I want you to notice something about this relation. So notice that they come in pairs. So for every ordered pair, I can sort of relate that to another ordered pair. So I have -2, 0, and I also have 0, -2. I have -2, -1. I also have -1, -2. I have -2, -2. There's nothing associated with that because it's its own reverse. -1, 0, 0, -1. 0, -2, -2, 0. 0, 1, 1, 0. So you can do this for every ordered pair. That is, this relation has the property, R has the property. How do I describe this relationship that's going on with these? Has the property that, so I could say it like this: if A is related to B, then B is related to A. This is called symmetry, or the symmetric property of a relation. So I could also write it if AB is in the relation, then BA is in the relation. So this relation has that property. Not all relations do, but this one certainly does. So we say that this relation is symmetric. What other neat property does this have? Well, notice that every element is related to itself. So -2, notice that -2 is related to -2, -1 is related to -1, 0 is related to 0, 1 is related to 1, and 2 is related to 2. And so R has the property that, how can we write this using logic? Well, I'm saying something about every element in the set, right? So for all A in S, so what's true about every element in S? It's related to itself. A is related to A. That's true for every single element. This is called reflexive. So we would also say that this has the reflexive property. Everything's related to itself. All right, let's move on and talk about a third property. So we already talked about these first two properties. If a relation is reflexive, what's true is that for all A in the set, I should say here, let R be a relation on a set S, then the relation being reflexive means that for every element of the set, A is related to A. Alternatively, you might write equivalent to the pair AA is in the relation. We talked about symmetry. This means that the following statement is true for all AB in S, for all pairs of elements in S. If A is related to B, then B is related to A. So if that happens to be true for every pair of elements, we say the relation is symmetric. And then lastly, we have this transitivity one. And I didn't mention in the last example because the last example it wasn't a transitive relation. So this is concerning triples of elements in S. So we could state it like this: for all A, B, C in S, if A is related to B and B is related to C, then A is related to C. So if we have these two things, A related to B and B related to C, we say it's transitive if it always follows that A is related to C. So a nice example of this would be like less than or equal to on numbers. Less than or equal to is a relation on numbers that is transitive, right? If A is less than or equal to B and B is less than or equal to C, then certainly A is less than or equal to C. And so inequalities in general are transitive relations. They have the transitive property. That might be a word that you've heard before, and now we're sort of adding to that vocabulary with these other properties. So at the same time, we should be able to recognize when one of these doesn't happen. And so it's useful to think about the negation of each one of these. So reflexive, symmetric, and transitive, that's what tells us if it's true. What tells us if it's false. So I'll write these in red. I'll say not reflexive. What would this mean? Let's negate this statement up here. This would be there exists an element A in S such that A is not related to A. And if we want to say not related, we'll just write an R with a cross through it. And that would be the same thing as saying there exists an element such that the ordered pair AA does not show up in R. There's at least one element that isn't related to itself. What about not symmetric? So here we're negating an implication, a universally quantified negation. So not symmetric, this would be there exists a pair, A, B, in S, such that A is related to B and B is not related to A. Notice the negation of the implication here. If then turn to and I negated the conclusion, B related to A. And then not transitive, well, this would mean I can find a triple A, B, and C in S such that, again, keep the hypothesis the same. A is related to B is related to C, and it does not follow that A is related to C. So A would not be related to C there. So those are those three properties that we're honing in on. Why? Because if a relation satisfies all three of these properties, then some special stuff happens. So we give a name to it. Satisfying all three of these properties means that the relation is called an equivalence relation. And like I said, some special stuff will happen. So we'd like to be able to recognize when a relation has any one of these properties, and in particular, when it has all three of these properties, because that'll be worthwhile. All right. When we had a relation in the last example where we could list out all the elements, right? It was a finite relation. There are only a finite number of ordered pairs to consider. It wasn't too hard to pick out the properties. But when we have an infinite relation, so a relation of infinite cardinality, it'll be a little bit more difficult. So this would happen maybe when we're dealing with a relation on an infinite set, like the natural numbers. So here we'll define this relation on the natural numbers by A is related to B if A is less than or equal to B. So I mentioned before that these inequalities are going to happen to be transitive. Well, let's see that, and let's see what other properties they possess. All right, so which of three properties does this possess? So we'll have to, since we can't just pick out and sort of exhaustively check all the pairs for the properties, we'll have to prove them by using logic and our knowledge of proofs. So let's take a look at symmetry. Actually, let's look at reflexiveness first. Reflexive. So is it reflexive? So let A be in the natural numbers. So given a natural number, is it true that A is related to A? So therefore, is it true that A is less than or equal to A? Yeah. Then A is less than or equal to A. What does that mean? Hence, A is related to A. And so that proves that it's reflexive. That's the only thing we had to notice here is that, yeah, I mean, that's a given. Every natural number is less than or equal to itself. In fact, it's equal to it. So it's definitely reflexive. What about symmetric property? Is it symmetric? Well, we need to ask ourselves if we're given, so we need to prove that implication, right? If A is related to B, then B is related to A. So suppose A is related to B, then what follows is that A must be less than or equal to B by definition of our relation. So can we conclude from that B is less than or equal to A, right? We'd like to be able to conclude. We ask ourselves, is B related to A? That is B less than or equal to A? So if A is less than or equal to B, is B less than or equal to A? Or can we come up with a pair that fails that? So the answer is no, that won't happen. If A is less than or equal to B, it won't always happen that B is less than or equal to A. And so let's prove that it's not symmetric by picking out a pair. Let A equal, I don't know, 3. and B equal 10. Then 3 is related to 10 since 3 is less than or equal to 10, but 10 is not related to 3 since 10 is greater than 3. So that's what it takes to show something is not symmetric, is a pair such that A is related to B and B is not related to A. Is this transitive? I already talked about that inequalities will always be transitive. And why is that? Well, let's let A be related to B and B related to C. And let's prove that A is related to C. Then A is less than or equal to B. So just writing out what that means, and B is less than or equal to C. Hence, A is less than or equal to C, because that's how natural numbers work. If one's less than or equal to that, and B is less than or equal to C, then A must be less than or equal to C. And so this is transitive. So it's reflexive, it's not symmetric, but it is transitive.